Hi, I'm Chem's best friend. Today's video will be about Lewis dot structures, introduction to Lewis dot structures. If you are interested in private tutoring lessons, the information is on the screen below. Okay, let's get started. Today we will do an introduction to Lewis dot structures, and this was first developed by Professor Gilbert Lewis. And let's go to my screen to see what Mr. Lewis did. And Mr. Lewis came up with an idea saying each electron will be represented by a dot. So remember, this is each valence electrons. These are electrons in the outermost energy levels. So the first column, our alkali metals, have one valence electrons, and here is one dot. And then we have our alkaline earth metals, and they have two valence electrons. We do not worry about transition metals, so we're going to skip all of them. And then the next column, we have 3 valence electrons, and then 4 valence electrons, 5, and these ones are oxygen column, 6 valence electrons. Our halogens have 7 valence electrons, and noble gases have 8, except helium. Remember, helium is in the first energy level, can only hold 2, right? So we have our valence electrons represented as dots. Okay, so sometimes you might be asked about Lewis dot structures for ionic compounds, and here we go. So we have sodium with its 1 valence electrons, and here is chlorine atom. And what's going to happen? So what's going on is that 1 valence electrons, remember, goes from sodium to chlorine for its space. And you're going to have then sodium without valence electrons, and then chloride. So sodium ion and chloride ion. And here is our ionic compound. And here is our magnesium and oxygen for magnesium oxide. So each valence electrons goes to the spot available on oxygen right here. And we have here our magnesium ion that lost its 2 valence electrons, and oxygen gained the 2 valence electrons, and we have magnesium oxide. Okay, well, what happens if we have, let's say, calcium atom and fluorine atom? Well, fluorine, remember, has a space right here for only 1 valence electron. So if calcium gives its electron right here to fluorine, you need a second fluorine with its spot available for the second valence electron. So this is why we need 2 fluorine atoms, and here is our calcium fluoride. And we talked a little bit about formula for ionic compounds in a different video. But here is the idea of Lewis dot structures of ionic compounds, but this is not what they are used for. Lewis dot structures are used to explain covalent bonding, and they are going to be used for molecules to explain how electrons are shared between the atoms within a molecule. So there are rules that we will have to follow. So let's go here. So here is the rules, and I'm first going to read these rules to you. They are very important that we follow them. And then we will do some examples. Are you ready? So first one is decide which atoms are bonded to each other. Many times the central atom in a molecule is the first atom in a formula. Here is also my little hint for you. Nature loves symmetry. Think about it. Nature loves symmetry. If you can make a molecule symmetrical, do it. And the second hint is put the more electronegative elements on the outside. So the more electronegative elements, remember, they are the ones closer to fluorine. They will be on the outside. Okay, we're going to determine the total number of valence electrons. We're counting valence electrons for the atoms involved. If we are doing that diagram for an ion, like a polyatomic ion, we have to make adjustments. So if the ion is negative, let's say nitrate, we're going to add proper number of valence electrons. And if the ion is positive, like ammonium, we're going to subtract the proper number of electrons. You're going to then put a pair of electrons in your diagram for each bond between the atoms. And here is very important. we're going to complete the octets of the atoms from outside in. This is the trap. If students mess up on Lewis dot structures, it's because they don't follow rule number 4. They start dealing with the middle central atom. It will not work. It's going to all fall apart. Remember, octets from outside in. Okay? But remember, hydrogen can only hold 2 electrons, and that means hydrogens have to be on the outside. And the last one, the last rule, is we are going to then count and check how many electrons we have in place. If we have any electrons left over, they are going to go on central atom. If we don't have enough to complete octets for each atom, we will have to think about doing a double or triple bonds. We will have to share even more electrons. Okay, so these are the rules, and we're going to follow them in this order, and we're going to do some practice. Are you ready? So let's go. So here is methane, CH4. All right. So first, we're going to determine what's bonded to what. Well, we're going to put carbon in the middle because hydrogen has to be on the outside. It can only hold 2 electrons. So let's put our hydrogens on the outside. Rule number 2, we're going to add our valence electrons. Remember what we're adding? We're going here. We're going to add our valence electrons. So each carbon comes with 4. And then we have 4 hydrogen. Each comes with 1. We have 8 valence electrons to work with. We're going to put 2 for each bond. So 1, 2, 3, 4, 5, 6, here 7, 8. And I used up all my valence electrons. I'm going to see quickly if my octets work. So let's look here. Let's go around carbon. Does carbon have an octet? Does carbon have 8 electrons around it? Yes. So carbon has its octet filled. And now let's look at hydrogen. Does hydrogen have its octet filled? Remember, octet for hydrogen is 2. So yes, each hydrogen has its octet filled. So let's look quickly for each hydrogen. And yes, it works. So we are done. Look at that. Methane is done already. Yoo-hoo! Let's go. We have now water. Water is next. So we're going to put oxygen in the middle. And remember, hydrogen's on the outside. And let's count our valence electrons. Well, we have 2 hydrogen. Each comes with 1 valence electrons, plus 1 oxygen comes with 6. We have 8 valence electrons to work with. 2 for each bond. Okay. Now we're going to quickly count. And I have 4 more electrons left over. And we're going to do our octets from outside in. But each hydrogen, remember, can only hold 2 electrons. So I have my octets filled on my outside atoms. This is done. So any leftover electrons then go on the central atom. So I'm going to put it right here. 1, 2, 3, 4. And now I'm going to quickly check. Does my oxygen have 8? Does my oxygen have an octet? Yes. So right here, I'm done with water. See, it's not that hard, right? You just have to follow the rules. Let's go here. We have our SiS2, silicon disulfide, and let's do this. So we have our silicon in the middle. And why am I doing it? Well, nature loves symmetry, and sulfur is also more electronegative, so I'm sticking sulfur on the outside. Let's count our valence electrons. So silicon is in the same column as carbon. So we have our 4 plus 2 times 6. That's our 16 valence electrons. I'm going to stick 2 for each bond, right? And I'm going to work outside in. So my octets for sulfur first. So let's fill our octets for sulfur. And I'm going to now check. Let's check. Okay, this sulfur has 8. So it's great. Octet is filled. This sulfur has 8. Doing great. And when I look at silicon, and this silicon has 4 electrons. It would like to have 8, an octet filled, but it has 4. Okay, so I quickly count, and I used up all my 16 electrons, right? So I used up all of them. So now I have to think of a possibility of double bonds. So we're going to then take these, move them over here, and then take these and move them over here. And you're probably asking, well, why didn't I take both from the same sulfur, meaning like this? Why didn't I do this? And the reason I didn't do that is, remember, nature loves symmetry. And then we will later, in a different video, talk about formal charge. So nature loves symmetry. So we're going to do this. Si, S, S, and we move these electrons over. Move these electrons over. And then I'm going to actually put them like this. So if I left these electrons alone, so just to show you really fast, if I drew these electrons then here, meaning I just right now took these electrons and just moved them here. So they are right here, right now. I can leave things alone like this, and that's fine. But the electrons would like to be, they come in pairs, and they would have to be as far away from each other as possible. So chemists usually then move them to be on opposite sides of each other. So this will be it. So here is our molecule, and I'm going to do quickly double check. And now, really fast, let's check here. Does this silicon have 8 electrons around it? Yes. And does this sulfur have 8? Yes. And does this sulfur have 8? Yes. So I'm good. Now, here is this molecule. I want you to think about something. So sometimes it's really great to have some molecules memorized. It's going to make your life really easier. So this will be a little side note here. Maybe it's time for a little side note. So I ask my students to have methane memorized, to have ammonia memorized, to have water memorized, really, to have these Lewis structures, and to have carbon dioxide memorized. Now look, silicon is in the same column. Let's go here. Let's go here for a second. So carbon and silicon are in the same column. They have same number of valence electrons. And then oxygen and sulfur are in the same column. They have same number of valence electrons. So if you have memorized carbon dioxide, you will quickly recognize that I can swap the atoms which have same number of valence electrons, kind of like Lego blocks. I can quickly swap them. So this molecule is the same as Lewis dot structure for carbon dioxide. It's a really good thing to have some of these memorized. The other one that I think you should know is these guys, F2, O2, and N2. And the thing is that this one we have a single bond, and O2 double bond, and nitrogen N2 triple bond. It's just really nice to have this done. Okay, let's keep going. Let's keep going for one more. We have CCl4, carbon tetrachloride. And, well, we'll stick carbon in the middle, chlorine on the outside because chlorine is more electron negative, and nature loves symmetry. So we will stick carbon here, 4 chlorines on the outside. And let's add our valence electrons. So carbon we have 4 plus 4 times each chlorine comes with 7. So we have our 32 valence electrons, and we stick 2 for each bond, and then we're going to work our way, remember, octets outside in. So let's quickly do our octets for each chlorine. And we do quickly double check. So I used up all 32 valence electrons. Let's check if our octets are filled. And here we go. Carbon, yes, nicely 8 valence electrons around it. And okay, here is chlorine, 8. This chlorine, 8. this chlorine has 8, and this chlorine has 8. So every element here has our octets filled. I used up all my valence electrons, and there we go. So I hope you like this introduction, and I think we're ready for more advanced Lewis dot structures. That will be in the next video. So thanks for watching, and see you next time.